Okay, statistics, optimization theory, and then fear of losing jobs to all robots taking all the world and all of that. How did that happen? How did we get to this point? Well, let's try and see. Notable urban legend, 1966. Marvin Minsky, that's how the legend goes. Marvin Minsky, MIT Turing Award winner of 1969, and 3 years after this, hired a first-year undergraduate student and assigned him a problem to solve over the summer. Connect the camera to a computer and get the machine to describe what it sees. Well, 60 years later, we can claim we solved the problem. But as everything goes, this is just an urban legend, and in fact it wasn't Marvin Minsky, it was Simon Papert, and hired a team of 10 students, and there is online, if you follow the link in the slides down below, there is an online explanation of the program of what needed to be done. But that's basically the computer vision computer vision research program for summer that took computer vision 60 years to realize, thanks to the recent development. But this is not uncommon in anything computer sciences do, like this XKCD comic tells us. When a user takes a photo, the app should check so that's the customer says, when a user takes a photo, the app should check whether they're in a national park. The programmer, sure, easy, a GIS lookup, so Geo-Informational System, give me a few hours. And the customer says, and check whether the photo is of a bird. And the programmer, well, I need a research team and 5 years. 5 years, okay, sometimes it's 60 years, as we just saw. In computer science, it can be hard to explain the difference between the easy and the virtually impossible. So what helped? ImageNet challenge. Fei Li, a professor at Stanford, and her group established store of labeled images with 14 million images and about 22,000 categories for each image, and established a competition. All of the images were found via web searches for WorldNet noun synsets, hand verified using Mechanical Turk, so people looked at everything and labeled everything. Bounding boxes were provided by the organizers and by Mechanical Turk, I assume, for query object that were labeled. For example, not just, okay, there's a bird in the picture, but also, okay, in this bounding box, the bird is in the picture. And new data was added for validation each year. And the competition was running for a while, and the error was 26%, as on the far left here, or around 25, 26, maybe 30. And it was slowly, year by year, by percentage point, crawling down. In 2012, Alex Krajewski, a student of Jeffrey Hinton in Toronto University, published this paper, AlexNet. Well, it wasn't called AlexNet, it was just a CNN. Basically, the story goes that Alex convinced Jeffrey Hinton to start using GPUs, and he coded up GPUs, a GPU implementation of a convolutional neural network, and was running a classifier training on ImageNet dataset. So in 2012, they published a paper and took part in the ImageNet competition. Well, that was 50 years after the 1966 computer vision task given to a single student, as the urban legend goes. But this AlexNet paper almost halved the error, right? So it used to be 26% the error, and it became 16.4. So that's a huge drop, and it did get noticed. since then, since that moment, what happened is Alex and other people at Toronto University from the team established a company outside of the university to put intellectual property into. And Google and Microsoft start bidding for that company and started a bidding war. In the end, Google won, but it prohibited the people in the company. It's practically was an acqui-hire. They hired people, like graduate students who just graduated, Alex Kraszewski included, to work at Google in Google Brain division. And the price that they paid was so high, they told them not to disclose the price. Well, anyways, that was an explosion in the industry of deep learning. Of course, people were working hard on neural networks and other things and on machine learning, as you know, since the 50s. But industry successes were variable. In any case, since AlexNet, the CNN that Alex used was invented in 1998, by the way, not in 2012. So we all are standing on shoulders of giants, or on a tower of many lemmings, like ourselves, right? Like myself. But the point is that by 2016, in a it's just 4 years. This is nothing on the geological timescale. But by 2016, the error from 26 in 2011, it got to 3.1, GoogleNet v4. So lots and lots of things have happened since then, and we will cover some, but most of them are attached to convolutional neural networks and architectures and large-scale computation. But anyways, it's a huge change, and it's a large shift, tectonic shift, I would say, in industry, where words like AI became commonplace, and it became customary to talk about algorithms replacing humans, which actually we can do. Like I worked in industry at a company for a year, replacing a lot of human labor. A company in US was hiring a fleet of human raters in India who were looking at a bunch of medical documents one by one as they stream from faxes and labeling accurately different points on the documents, like patient, provider, dates, and all other entities, and putting them in database. And that was a tedious and expensive labor because people had to do it. So in a year of work with a team of 5 people, we were able to automate it almost completely. Just with some corner cases, maybe 5% corner cases left. So the fears for jobs that are not creative, don't require thinking, are real. And if you are planning for a job where you would just use your visual system and never think or invent anything, then maybe you should reconsider your career choices, because people like me and my graduate students will try to automate those jobs. So, and I hope you will get excited enough by this class that you will try to automate those mundane jobs, so humans can work on more interesting, more challenging, and more useful tasks. Remember the first slides, we need to go to space. So a little more history of the revolution for ImageNet. PERCEPTRON, 1958, Rosenblatt published a paper where this simple linear threshold classifier was introduced, and it's just a sum of the inputs with an additional bias term. Our bias input is always 1, and weight is what changes. That's how hyperplane gets moved around, and what we get an algorithm that is able to separate two classes of points if the linear separating plane or line in this case exists. And so those are actual iterations of perceptron convergence algorithm. We will cover this algorithm in class in great detail. And then immediately people started talking about stacked perceptrons. If we can connect multiple perceptrons into a deeper network, then we can solve much more complicated problem, because immediately after introduction of the perceptron, or very close, since Marvin Minsky and Simon Popper published a book called Perceptrons, where they proved that a perceptron is unable to solve certain large classes of problems, like XOR problem or XOR and well, parity problem. So the networks with stacked perceptrons are able to solve all of those problems, and modern version of those stacked perceptrons is the deep neural net that you all probably heard about if you don't know how to work with it. The one on the picture is so-called feed-forward neural network, and it's just a bunch of linear transformations followed by nonlinearities, pointwise nonlinearities with categorical, I guess, output, but it can be regression as well. Convolutional network is a little different in the sense that it introduces an inductive bias, a specific inductive bias for images, assuming that images contain translation invariant pictures. For example, if there is a cat in the picture, the cat is a cat, doesn't matter if it's in the upper left corner or lower right corner or somewhere in the middle. The same we could say about edge detection. The edges, counter clockwise edges, or vertical, horizontal edges, they're still edges, and no matter where they are in the picture. So interestingly, this inductive bias, biasing the whole model to images, has recently been shown to do surprising magic. That if you take, say, a feed-forward network and and images and try to classify them by not training, by simply randomly initializing feed-forward network, then you get garbage out. But if you carefully randomly initialize a convolutional neural network without training, you still already from the beginning can get good accuracy. So another thing with convolutional network, at least the one on the picture, and I think this one is pretty close to AlexNet that won in 2012 ImageNet competition. The interesting part is, or two parts, right? We have, I'm trying to write on the screen, but it is not working. Maybe next time. But what I'm trying to say is, look at this. This part is fully convolutional. It only consists of convolution layers, but then it is followed again by a feed-forward network. We will talk about this part closer to the end of the class, that you don't always need feed-forward connections here at the end. You may get by with just the convolution part or fully convolution for some networks. So that's one type of inductive bias for images that have spatial correlations and spatial structure inherent in them. But there are also time series and sequences, such as speech, such as text, language, and many other sequential data sets, time series and science as well. And here comes recurrent neural network, RNN. RNNs are super powerful Turing-complete machines. They can do, or they can compute anything computable, basically, and in theory can solve all computable problems. They just may not always be the most efficient because of the recurrent step. The next step of the computation can only be completed once the previous steps are done, unlike convolutional neural networks where everything can be parallelized. But still, recurrent neural networks are important model and powerful model. We should never overlook their power, even if transformers or any other neural networks available at the end of the day seem to be more powerful and seem to be solving or dominating until at least the landscape. The trick about everything that I just told you is that all of those successes in industry, at least, and some in academia, can be attributed purely to supervised learning. Since 2012 and acquisition of the company with Alex Krzyzewski and Jeff Hinton, what we have as the field perfected is supervised learning. Of course, many other attempts and efforts are created, like variational GANs for Bayesian optimization, like variational autoencoders, like generative adversarial networks and things like that. But still, the best thing that we can do is backpropagation and supervised learning when we have X sub I for each sample, the data, and we have Y sub I, a label for this sample. There is more to machine learning than just supervised learning, and there have been recent successes as well that I want to cover that go beyond that.